Hello, Chem 212 students, and welcome back for this week's videos about Chapter 9, Alkynes. So in this chapter, we're going to learn some brand new reactions. Some of the most important ones are going to be those that allow us to add more carbon atoms onto a molecule. We have not seen reactions that can do that yet. But alkynes will give us that possibility due to some of their special properties, in particular, their ability to donate a proton, which is not, there is much more prevalent than it is in alkenes and alkanes. And so let's get started talking about alkynes. Alkynes are molecules that possess a carbon-carbon triple bond, as you guys know from when you studied functional groups in the first chapter. So a triple bond is composed of one sigma bond in which there's direct overlap between sp hybridized orbitals. And we've got two sp hybridized orbitals here, one on each side of the carbon in gray. And we have one sigma bond between the overlap of the sp orbital and the two carbons, and then an overlap of the sp orbital with the 1s atomic orbital in the hydrogen atoms to make this sigma bond. In addition to the sigma bond, there are two pi bonds that are 90 degrees from one another, and these involve, of course, the sideways overlap of unhybridized p orbitals. And so since it's sp hybridization, that leaves two unhybridized p orbitals that can be involved in pi bonds. So the take-home message here is that a triple bond is composed of a sigma bond and two pi bonds. So when it comes to alkynes, they're similar to alkenes in the fact that they have pi bonds. And the electrons in these pi bonds, you can see they're a lot further from the nuclei than those that are involved in the sigma bonds. And so it's much easier for them to be removed. And so those electrons in the pi bonds can act as a nucleophile, as they did in alkenes in the previous chapter. And so many of the addition reactions that we studied in relation to alkenes will also work on alkynes, but there will be additional considerations due to the fact that there are two pi bonds in the carbon-carbon triple bond and not just one. When it comes to alkynes in industry and nature, they're relatively uncommon, although there are a few interesting examples. Acetylene, or also called ethyne, is the simplest alkyne, and it's used in welding torches, so it burns at a very high temperature, which is useful for welding. There have been more than 1,000 different alkyne natural products isolated. This is much fewer. There are probably millions, or at least hundreds of thousands of alkenes that exist in nature, but about 1,000 alkynes. One example is this histrionica toxin, which exists in frogs, I believe it is, and it has two carbon-carbon triple bonds here, two alkyne groups. Another very important example is that used in the birth control pill. And so the birth control pill is an analog of the structure of the female reproductive hormone. However, the difference is that there is a carbon-carbon triple bond here, and that makes this far more effective in inducing the menstrual period, and therefore it's used in birth control pills. So in terms of the naming of alkynes, it's very similar to the naming of alkanes and alkenes. Like the alkenes, if you have a carbon-carbon triple bond, you want that to be a part of your parent chain when you're naming it. And then you're going to look for the substituents that are not that are attached to the parent chain but not a part of it. You'll assign a locant, and like we did with the carbon-carbon double bonds, if you have a carbon-carbon triple bond, you're going to start numbering from the side that is closest to the carbon-carbon triple bond. Then you'll list the substituents in front of the parent name in alphabetical order, ignoring prefixes, just like before when naming alkanes and alkenes. And finally, just like with alkenes, you can place the locant before the parent name or just before the "-ine" suffix. So if we have a couple examples here, so these are completely analogous to the alkenes, so I won't spend too much time on it. You can see that in terms of the naming, the difference in the naming of the parent chain is that if we have no double bonds, we end with ane. Here, pentane, 5 carbons with no double bonds. If we have a double bond, we say pentene, and we need a locant to indicate where the double bond is. Here it's on the first carbon. And then finally, if we have an alkyne instead of carbon-carbon triple bond, we end the parent chain with -ine. And also, again, like the alkene, we have a locant to say where the triple bond is beginning. And here it's on the first carbon again. And just like with alkenes, if you have a longer chain that does not contain the alkyne group, so for example here, if we made the horizontal chain here the parent chain, that would be called octane. However, it would not contain the carbon triple bond, so that would be not the valid parent chain. The valid parent chain would have to include the carbon-carbon triple bond. So the parent chain here would be heptyne, ine because it contains the triple bond, and hept because there are 7 carbons in that chain. 1, 2, 3, 4, 5, 6, and 7. So given that, even though there was a longer chain without the triple bond, because it didn't contain the triple bond, it could not be considered the parent chain. We have to include the triple bond. Next, we're going to identify and name substituents in a name. So here's a different example. So let's go through step 1 first. So in step 1, we find the longest chain that contains a parent chain, and it would be going right along here. Whoops. Right along here. 1, 2, 3, 4, 5, 6, 7. You would not number from the right side. 1, 2, 3, 4, 5, 6, 7. Because then you would only reach the carbon-carbon triple bond once you got to locant 5, but you want to start numbering on the side that's closer to the carbon-carbon triple bond. If we number from the left, we get to the carbon-carbon triple bond at carbon number 2. And so now we've assigned the locants. We should look, so our parent chain here in this case would be 1, 2, 3, 4, 5, 6, 7. It would be 2 heptyne would be the parent chain, and then we've got 3 substituents here. They're all methyls, 1 here, and 1 here. So we have a trimethyl, 3 methyl substituents. So when we name it here, finally, we're going to list the numbered substituents. There's only one type, it's methyl. So we say trimethyl. And since we're numbering from left to right, 2 of these methyls are going to be on the 5th carbon, 1 is going to be on the 6th. So we say 5, 5, 6 trimethyl, and then 2 heptyne because the triple bond starts on the 2nd carbon. We could also say hept2-ine, and sometimes that's often done when there's 2 important functional groups, and so the other functional group can have the number in the front. But either of these are equally acceptable, so you can do either one. And notice, one thing I want you to notice too is when drawing the line structures of the triple bond, for the carbons that are involved in the triple bond, their bonds to other carbons or to hydrogens are often or should be drawn straight out from the carbon-carbon triple bond because the bond angle here is 180 degrees. So it's better if you properly represent that as best you can when drawing the line bond structure by drawing these bonds straight out in this fashion. So when it comes to common names, the common name for ethyne is acetylene. So ethyne being this guy right here. So we say 1, 2, 3. Ethyne. So that would be ethyne, right? There's a carbon here. We could, if we wanted to draw in the carbons, we could put the carbon here, the hydrogen. And this is often called acetylene. That's just an old name that's extremely common, and a lot of people use it. So you'll often see that there are other names for alkynes that are derived from this common name acetylene. Like if there's a methyl group attached, we call it methyl acetylene. Here there's 2 isopropyl groups attached to the carbon-carbon triple bond, so we call it, some people will call it diisopropyl acetylene. So it's sometimes common to name a alkyne instead of in the IUPAC systematic name as an adjustment where we list the groups that are in front of the name acetylene as those groups that are attached to the carbons involved in the carbon-carbon triple bond. This is something you might see here and there, but it's not our preferred way of naming, right? I always ask you to do the IUPAC systematic naming system when you're doing this. Okay. In terms of some terminology here as well, it's often useful to distinguish between internal or terminal alkynes. So terminal alkynes are different from internal alkynes in that there's a hydrogen attached to the carbon on the end, and this hydrogen, as we'll discuss, is significantly more acidic than those hydrogens that would be attached to an sp2 carbon involved in a carbon-carbon double bond, or sp3 carbon involved only in single bonds. So that would affect the way this kind of molecule reacts. So it's often very useful to distinguish between a terminal alkyne, such as the one on the left, and an internal alkyne, such as the one on the right, where there's no hydrogen attached to these carbons. So as I mentioned, as we learned in chapter 3, alkynes are significantly more acidic than are alkenes and alkanes. I mean, the pKa here being 25, they're not hugely acidic. In fact, they're not very acidic at all. They're on the lower end of acidity, all of these. They have quite high pKa's. But acetylene is, or ethyne, or any terminal alkyne is significantly more acidic than an alkene or an alkane or an alkene. And we can recall this based on our study of REO, the idea of REO. Let's go like this in chapter 3, and that is when we decide, when we take a look at the conjugate base of ethyne, rather, or other terminal alkyne where the hydrogen's been removed, the negative formal charge here goes on a carbon that is sp hybridized, right? This carbon is sp hybridized. And so this relates to the O in REO, or orbital. And because of the small size of the sp orbital, the negative charge is held more closely to the nucleus and better stabilized, making this ethyne or terminal alkyne significantly less reactive in terms of grabbing protons back than an alkene or an alkane. So you can see, the difference is 19 pKa units between an alkene hydrogen versus an alkyne hydrogen. And so these are significantly more acidic, and we're going to make use of that property of alkynes. So here's an example of a proton transfer related to an alkyne here. Again, this is explaining the stability of the deprotonated alkyne in terms of REO, this carbon being an sp hybridized carbon, sp. So when the proton is removed by a base, we need a quite strong base, and so we're going to have special bases that we're going to talk about today that are extremely strong, or in this lecture series. And you need a sufficiently strong base to remove a proton from the alkyne, but it can be done with a strong enough base. And so that's going to be a key part of the chemical properties of alkynes that we use synthetically. So again, here's a picture of the relative stability of the electrons in the sp3 orbital, which again is larger, and so those electrons on average are farther from the carbon nucleus, versus an sp2 orbital, which is smaller, versus an sp orbital, which is even smaller. And so those negative electrons there, these electrons are very close to the nucleus, which stabilizes and keeps them from grabbing a proton as easily as in these other alkenes and alkanes. So when it comes to the choice of a base to deprotonate an alkyne, well, our classic base in water would be hydroxide, right? That's our classic base. And so, if we were to try to remove this proton from the alkyne, and so we have a proton transfer here, this electrons go and grab this proton, make a bond with it, then these electrons are left behind, and we get this alkylide ion as the base, and the conjugate acid for the water once it grabs a proton, or for the hydroxide once it grabs a proton, is water. But we can see that water is a significantly stronger acid than ethyne here. And so this will favor equilibrium that will go much more to the left. And so you can see that by the larger arrow going left than the smaller one going right here. And so that's trying to represent that this equilibrium significantly favors the left side. It's almost a one-way arrow. You could really, according to the book's rules of a pKa difference of 2 or 3, that would be sufficient to give you a one-way arrow if you wanted to. But we're doing a little arrow here to show, yeah, it goes a little tiny bit into the right, but it goes mostly to the left. I mean, we got a factor of 10 difference in the pKa, so we're talking about, or at least 9. We're talking about 10 to the 9th power more of these molecules on the left side than on the right. So instead, what we need is a stronger base than hydroxide. And a common choice here is the amide ion, NH2-. So you can see this nitrogen has 2 bonds and 2 lone pairs, so it has 1 less bond and 1 more lone pair, giving it this negative formal charge. The sodium in each case is the counter ion here. It's a spectator and not involved. But this is sufficiently strong of a base to deprotonate the alkyne. And so we'll grab the proton, leave these electrons behind, and then what we get is the conjugate acid of amine, which is ammonia, NH3, no formal charge here. And then the proton was removed from the ethyne here, and then those 2 electrons here were left behind. So these are these 2 here. And in terms of the pKa now, the pKa of ammonia is pretty high. You wouldn't really commonly call it an acid itself. It's very difficult to remove that proton. It's a weaker acid than the ethyne itself. So in this case, the difference here being a pKa of 7, there will be 10 to the 7th power more of the products on the right here than there will be reactants on the left, which is why we have the little arrow going left and the larger arrow going to the right. And so the suitable base here for deprotonating the alkyne, amide, is a very common choice here. So now amide isn't the only base that can be used, and also ethyne isn't the only alkyne that can be deprotonated in this way. Any terminal alkyne that has a hydrogen attached to the carbon that's involved in the triple bond can be deprotonated, and any base can be used that is has a conjugate acid that is stronger than the alkyne itself. And the product here of the deprotonated alkyne is called an alkylide ion. So a sodium amide is often used as a base, but again, others can be used too. So here's a kind of select set here of bases and their conjugate acids. A subset of those that we talked about in chapter 3. So when it comes to the strength of the acid, so the ethyne here is a weaker acid than alcohols and water. Okay, so their conjugate bases here of these stronger acids will be their conjugate bases will be weaker bases. The stronger the acid, the weaker the conjugate base, because that acid wants to get rid of the proton more, right? And so these will be weaker bases than the alkylide ion itself, and they will not deprotonate the alkyne. Okay. However, if we look at hydride ion, amide ion, and these ions here with the deprotonated alkanes, these would be significantly stronger bases here than the alkylide ion, and these would deprotonate the alkyne. So we can see here that H2, hydrogen gas, is less acidic than, it's a weaker acid than the alkyne here, as is ammonia, as are alkanes. And so that means that the conjugate bases are stronger bases, And so these bases would be strong enough to deprotonate. So very commonly, these will be the kinds of bases that are used: amide or hydride ion, or a deprotonated alkane. So in the last chapter, we talked about, or in chapter 7, we talked about elimination reactions that can be done in order to produce an alkene. So if we react a alkyl halide with a strong base, we will initiate, probably in this case, it would be a E2 reaction, and that would produce us a alkene. However, we can't get an alkyne that way because we would have to do the same thing twice, essentially. So what we need is a dihalide, so that we can do an elimination and then an elimination again. And what's interesting about this too is because of the geometry of the alkynes and their triple bonds, what we're going to see is that the mechanism will be significantly different than that for the elimination that produces just the alkene. So let's take a look at the details of this elimination. So such eliminations will occur, like I said, usually by a E2 mechanism. And when it comes to dihalides, there's two possibilities. We can have a geminal dihalide. Geminal here refers to the fact that the halogen atoms are attached to the same carbon atom. And so if we have a geminal dihalide, we can have a base here that can grab the proton that is positioned anti-periplanar. It would have to be just like an E2 reaction, anti-periplanar to the halogen. If you got two halogens, that's not such a big deal. So we remove the proton here. These electrons go into making the pi bond, and simultaneously the leaving group leaves. A standard E2 mechanism. When it comes to a base here, then we have the alkyne here, and we can have a second elimination here, E2 style. So the proton again is removed. Then these electrons go into making the second pi bond for the triple bond, and the leaving group leaves. And so we can get the triple bond here. With a vicinal dihalide in a similar manner, we can have an E2 reaction to produce the base. Now, that said, in terms of mechanism, there's a little bit more to say here. And we're going to get into that in a moment here. Sorry, I'm just kind of refreshing my mind a little bit here. So we'll talk about this in a little bit more detail. But it's safe to say that we can say that this elimination occurs in an E2 style. Okay. If we have notice that we need to have enough base to deprotonate twice here. Okay. If we have even more base, the product here that base can then go on to, if it's a strong enough base, to deprotonate the alkylnide ion here. And so excess equivalents of sodium amide here can be used to shift the equilibrium towards this elimination product. So we use a lot of base. We can really push this reaction to produce the triple bond. And what happens if we use an excess base? We have extra base left over, and assuming that base is strong enough, it can deprotonate this carbon and produce the alkylnide ion. And so if we use a excess of strong base to get the alkyne itself, we'd have to reprotonate it. And one way to do that would be just to expose this to water, because again, water is a stronger acid than the protonated alkyne. And so if we add water afterwards, after we've done our production of the alkylnide ion here, we can protonate that alkylnide ion. So again, we have a proton transfer. The lone pair here on the alkyne grabs the proton, and those electrons are left behind in this bond, and we get a hydroxide ion and the protonated alkyne. And this equilibrium favors the right quite strongly, because the alkyne is a significantly stronger base or acid than the water. So this goes stronger acid over to the weaker, and stronger base over to the weaker base. So one word kind of what do you call this? Shorthand that we're gonna use is when we use more than enough of a particular reagent, we'll say that we've used excess, and sometimes that's abbreviated XS. So we can say XS sodium amide, and then followed by water to protonate the alkyne, so that we get the protonated alkyne. And so that's the reaction sequence that you'll see to get the protonated alkyne in the end. A subsequent follow-up with water after the double elimination that occurs here. Likewise, previously with the alkenes, we had seen the hydration, or the addition of hydrogen atoms to each of the carbons that is involved in the double bond. Likewise, we can do this with a triple bond, but again, we'd have to do this twice, so we'd need twice as much hydrogen, or 2 equivalents, to get the alkyne here. When it comes to the addition, remember that this occurs when we're doing catalytic hydrogenation on a metal surface like platinum. This involves a cis addition, syn addition of the hydrogen, which will produce, with the first equivalent of hydrogen, a cis alkene. And so, but given that usually there will often be an excess of hydrogen, this will go on to quickly produce the completely hydrogenated form here, where the triple bond is no longer there. We added 2 hydrogens, got a double bond, and then we added 2 hydrogens again, and then it's a single bond. And we've added 4 hydrogen atoms altogether, 2 on each carbon. Now that said, sometimes we want to stop this hydrogenation when we get the double bond. And so when we do this, we'd want to use what's known as a poisoned catalyst. The poisoned catalyst is one that allows for the addition of the first equivalent of hydrogen to get the alkene, but not the second equivalent to get the alkane. A commonly used poison catalyst is Lindlar's catalyst. And so this is going to produce, here's what Lindlar's catalyst is. It's got a palladium surface, but it also has this quinoline involved in it as well, barium sulfate, and then methanol. So this is just generally, this combination of reagents is referred to as Lindlar catalyst. And so the reason why this works is the Lindlar catalyst is set up so that it will catalyze the first hydrogenation and help with that, but it will not catalyze the second hydrogenation with the poison catalyst. And so we get a very quick transformation of the alkyne to an alkene, but the addition of hydrogen to produce the alkane from the alkene goes very slowly. And so we get a significant amount of the alkene without the further hydrogenation. If we want to produce, so notice again that the use of the Lindlar's catalyst, the poison catalyst, produces the syn addition of hydrogen, where the hydrogens are added on the same side. What if we want the trans addition? So the trans addition will have to go through a different mechanism, and the reagent and the kind of reaction that's used for that is referred to as a dissolved metal reduction. And this reduces the alkyne to a trans alkene instead of a cis alkene. And this proceeds through a radical reaction mechanism. So we're going to be discussing radicals in the next chapter. But the sodium is a sodium atom. It's sodium metal. So remember, sodium is group 1. So it has 1 valence electron, an unpaired electron, which is going to help us initiate a radical chain mechanism. Radical referring to molecules that have unpaired electrons. So we'll use sodium, and the solvent here will be ammonia. And so this is stereoselective for the anti-addition, so we get the trans product here, where the hydrogens have added in the anti-configuration this time. And this is going to be our first exposure to a radical mechanism. We're going to see a lot more of this in the next chapter. But what you'll notice about this mechanism that I'm about to show you, which is it's kind of a combination of an ionic and a radical mechanism. This mechanism is going to involve the use of single-headed arrows or fishhook arrows. These are used when one electron is moving rather than two, and we're going to see a lot of that in the next chapter. So this mechanism is initiated by the fact that the sodium is giving its one electron to this carbon here. And then one electron from the pi bond also goes on to this carbon. So this carbon now has a lone pair to it with these two electrons. The other electron from the pi bond goes on the neighboring carbon. And so we have a radical here and an ion. So we have an ion radical. The next step involves a proton transfer. And so this pair of electrons here goes and grabs a H plus, a proton, and those electrons are left behind, leaving us an amide ion in the solvent. That said, there's lots of ammonia, so having a few amide ions does not make a huge difference here, especially since it's not a strong enough base to deprotonate an alkene, so we don't have to worry about that. Only alkynes, and we no longer have an alkyne, right? Now what we have is a radical alkene. And so now we have an unpaired electron here. Another sodium atom comes and gives one more electron to give us this negative ion, which can then go and deprotonate another ammonia. Again, we're doing this in ammonia solvent, so there's plenty of this around. And so we can deprotonate ammonia and get the amide ion. And again, this works because the amide ion is a weaker base actually than this sp2 carbon with the lone pair in it. If we were to talk about the pKa of this, the pKa is about 44. pKa equals 44 here. Oops, behind my head, 44. And here the pKa for the ammonia is about 38. So we can see that the ammonia is the stronger acid out of these two. This is the weaker acid, so it's going to give its proton, and this will go forward quite nicely. So let's talk about each of these steps individually. So in step 1, the sodium atom with its one electron is transferring that to a carbon, and that's how we get this negative ion here. Again, note the use of the fishhook arrows to show the movement of that single electron. Each of these is the movement of a single electron. Now, what causes this to add the hydrogen in the trans position rather than the cis one, to do the anti-addition rather than the syn addition, is that the electron here that is involved is in this orbital, and the electrons that are in these are sp2 hybridized orbitals here. These repel one another. They don't want to be close. And so the lower energy structure is going to be the one that puts these electrons on opposite sides. And so this is going to prefer the electron here, this electron going into the orbital position opposite of this one. So they adopt this anti-geometry. And at that point, then we have a normal proton transfer from the ammonia. The weird step that's new is we get the movement of one single electron again to turn this, instead of being a radical with an unpaired electron, at that point it becomes an ion with a negative formal charge, because this carbon will have 3 bonds, 2 in the double bond here, 1 in the single bond, and two electrons in the lone pair. So it will be a carbanion at that point. So we have a carbanion, and then this goes and deprotonates. So this is a kind of our first taste of a radical mechanism. It's not completely a radical mechanism. There are also ionic parts. We can see here we have ionic parts. We're going to have some mechanisms in the next chapter that don't have ions at all. They're all just radicals until we get a final neutral product. So when it comes to hydrogenating a triple bond, we can, if we use hydrogen and platinum, the advantage is if we have enough hydrogen, we'll need 2 equivalents, we can go straight from the triple bond to the single bond. However, what this means is we can't stop there. So if we want to stop and have a double bond, if we want to stop in the middle before we double added the hydrogen, we need to use a poison catalyst or a dissolved metal reduction. If we use the poison catalyst like Lindlar's, we're going to get the cis addition of the hydrogen, and if we use the dissolved metal reduction, we're going to get the trans product. And then, as usual, if we want to hydrogenate the alkyne, we can always use hydrogen with platinum catalyst. So that's going to be it for this first video for this week. As we come back for the next video, we're going to begin to talk about asymmetric additions now, in particular hydrohalogenation. So when it comes to hydrohalogenation, we have to think about not only the stereochemistry, but also the regiochemistry. Where is the halogen atom going to go? And where is the hydrogen atom going to go? Because now it's asymmetric. We're going to add hydrogen to one carbon and halogen atom to the other. So that will be the topic. So in this video, we've covered hydrogenation of the alkenes. We've covered the production of the the production and the deprotonation of the alkynes. And so in the next chapter, we're going to start to talk about the other reactions that are common and useful for alkynes, starting with the hydrohalogenation. I'll see you on the next one.